Presented here are slides of our second major VR project on outlier detection, and this work is appearing in the Journal of Chemometrics. Presented in this work is our outlier cleaning for quantitative analysis purposes. And in quantitative analysis purposes, we have our Y vector of our training samples of known reference values. And so these, in our case, will be analyte amounts, is what we call them in analytical chemistry. And then in the X are our measured training spectra, our calibration set also. And these can be IR, near IR, any one of our number of spectroscopic methods. And then we have our regression vector B for our model. And then we need a pseudo inverse on that training set. We typically use partial least squares to get that to obtain an estimate of our model vector. Once we have our model vector B hat, we can then inner product that with our new samples, our target samples that we want to predict the analyte amount. Problem with autonomous algorithms are that do outlier detection they're very rigid, and they're rigid because they have preset thresholds to determine if a sample is an outlier or not. Where we're going to use our VR, which is much more flexible, nothing's hard set in stone, and the human will do the reasoning to decide if a sample is an outlier or not, in spite of the magnitude of the outlier measure value. We have two types of outliers, X outliers, and this is where the sample spectra have reference values spanned by the training set, but they're substantially different relative to the X value. And these would be our high leverage samples. Then we have our Y outliers, and these are where the sample analyte reference values don't correlate with the spectral trends. So then when you build your model and you use to predict these samples, they will have a large prediction error. In other words, they'll have a high residual. We want to be able to identify these two types of outliers. Outlier cleaning issues that are visible in virtual reality, we can actually see when this is occurring, which is another advantage of the virtual reality, is swamping and masking. Swamping is when outliers cause normal samples to appear as outliers. Problem with autonomous algorithms is because of their thresholds, they can falsely label a swamp sample as an outlier. Masking, outliers cause other outliers to appear as normal. And again, the problem with autonomous algorithms is because of these thresholds, they can falsely label the masked outlier sample as a normal sample. So in VR, as we'll see, we use this iterative flexible process, and so the user can remove any suspect sample from the training set in VR, and then the whole VR landscape reconfigures, and then we can assess for masking and swamping. And then depending on what our decisions are, we can return that sample back to the training set and we can test other suspect samples. In order to represent our samples or objects in virtual reality, we need to create what are called the sample glyphs. And so we're going to use these physicochemical responsive integrated similarity measures that we created. And these measures, we create hundreds of them, and they're sample-wise. So every sample will have hundreds of prism values that then we can correlate to the features on our glyphs. And then we also, in the original paper, we combined these values to produce a quantitative sample similarity z-score. And we're going to do the same thing in this paper. So every sample in the VR will have a z-score value relative to the training set z distribution. And we have three types of prism values. We have our prism X values based on spectral measures, which we're going to use to identify our X outliers. And we have our prism Y values based on the estimated analyte amounts. And these are what we will use to identify our Y outliers. And then we can also look at the composite of the combination of the two. So these are our sample glyphs in virtual reality that you'll see in the movie. So we have blue will always be our Prism X glyphs, red are our Prism Y glyphs, and the composites are represented by 3. So you can see our samples are represented as spheres with a lot of spikes. And for the Prism X values, we have 316 outlier values, and so you can see the blue ones has a lot of spikes, and the bigger the spikes, the more dissimilar that sample is to the rest of the calibration set. And then we have 80 Prism Y values, similarity values, and then the X and the Y's are combined to form 80 Prism comp outlier values. So they have 80 spikes. The size of each of these spheres are relative to the z-score, and as you'll see, we can change to the conformal prediction p-values we set up into the algorithm as well. And then to help us see the difference between large and small, we also color shaded the spheres relative to their z values. So if they have a small z value, you can see these are very light colored, and they're medium colored here for medium size, mid-range z values. And then we have very dark colors for the large z values. And then over here, you can see what else we can do in the VR. As you'll see, if you touch a glyph, you'll get the sample number and a ZP score. So we get the Z value 4.2 separated by a slash with the conformal prediction P value, which then you can also use to assess, probability of a sample being part of that training set. So we also need a spatial coordinate system in the VR. So we're used to, because they both provide unique pieces of information. One of them is principal component analysis, very commonly used. And so we have this user interface, and you can see the slide bars allows us to pick any one of the rank X of the PCs to be one of our axes labels. We also have some toggle switches in there, the scale method, that's for range scaling or auto scaling the spikes on the glyphs. And then the other active drop-down menu here is the size method, so we can flip between the z-score, like I said, or we can do the conformal prediction p-value. These other group method, color scheme, and this analytic scoreboard, that's for our ongoing classification work. So it's a similar software. So we're kind of doing outlier detection with the classification software. So this is a quick video of what the demonstrating the UI for the PCA. So here we can slide around. You can see the score plot changes depending. Doesn't change a lot as we change from 1, 2, and 3, because PC 1s, 2, and 3 pretty much characterize the bulk of the information. But that's not true for all data sets. So we can adjust the axes as we want, and it'll change the spatial relationships for helping decide if a sample is an outlier or not. The other spatial positioning is UMAP, and that's for uniform manifold approximation and projection. So we can see we have 3 slide bars and the same drop-down menus and analytic scoreboard for the classification work. So we're using UMAP for classification as well. The first slide bar is number of neighbors, and that constrains the local neighborhood. We have 10 values automatically set in that slide bar from 5 to 50. And then we have our distance value. We have 10 values set in there from 0 to 1. And then we have our distance matrix, like Mahalona distance, Euclidean distance, Manhattan distance, and so forth. And there we've put in 6 of the measures in there. Another aspect of UMAP is another tuning parameter are the number of components, and that sets the dimensionality of the reduced dimension space that you're going to embed into the data. Where we don't make that a slide bar, we just default set that to 3, and so we'll just have our 3D UMAP plot, but the spatial positions will change depending on number of neighbors, distance value, and distance. So this is a little video of that. And so you can see the relationships, the spatial positions change dramatically depending on that. And so that will significantly help in our identifying local clusters, whether a cluster is an outlier cluster or within a cluster, is there an outlier sample in there or not, by changing the local clustering there. And you can see all the prism X, prism Y on the peripheral also change as we change any one of those UI control bars. Okay, so like I said, we have a successive outlier cleaning step. So we're going to use in the VR the shape of our, based off the number of, or the lengths of the spikes, the spatial position, the z-score and p-values for the sizing to decide if a sample is an outlier and if swamping or masking are present. I don't have a video showing the swamping and masking identification, but in our paper, we have that attached into the paper, and we show a couple situations where we do have swamping and masking and what that looks like in the VR and how you can remove a sample and put it back and so forth. But even in the general outlier and cleaning steps, we can remove a suspect sample. Like I said, we recalculate the PCA UMAP and all the prism values. It gets all recalculated because now we're missing a sample. And then we reassess the new landscape for any new samples or what was the effect of that sample that was removed. And then we can replace that sample or continue on if we decide it's an outlier and continue on to the next suspect sample. And then we don't stop when it based off some hard threshold. We stop when it appears to the user that the remaining samples are not outliers. And like I said, that can be in spite of the fact that you do have some larger z-scores or conformal p-values. So obviously you might be thinking that, hey, there's going to be some biases here, but you know what? Computers have biases too, believe it or not. So the human, yes, the path through this VR landscape is going to depend on what which user is doing it. And because humans are biased to what they expect or what they want to see. But we think there will be agreement on what is obvious large outliers and obvious swamping and masking situations. That'll be more black and white type decisions. The deviations from person to person, the human biases will come in on those gray borderline situations. But we think we can circumvent that or get more common agreement from person to person because of our iterative process. You can remove samples and put them back for further assessment. And so those gray situations, we can see what the effects are by keeping the sample in there or removing it. We can switch to the UMAP with multiple projection views, and actually in the paper that is what goes on in one of the borderline situations. Couldn't decide if sample A or sample B should be removed, so we went to the UMAP, and that's all shown in the paper to make those decisions. And then we can always look at the z-scores in conjunction with p-values relative to what the population distributions are, where those values lie with respect to the distribution. Okay, computers, their decisions are rigid, but they have human biases because the human has to pick which algorithm they want to use. Every algorithm is going to select different samples as outliers. And the choice of these thresholds that these outlier algorithms make their decisions on are also set by the human. So there's just as much bias in software, autonomous algorithms, as there are in a VR human decision. For our example VR of outlier cleaning, the data set will be this cornmeal data set. We have 80 samples measured on 3 different near-IR spectrometers, and we had 4 analyte properties: moisture, oil, starch, and protein. The VR movie will be on the moisture property. And after every time we do remove a sample, we go ahead and before everything is recalculated and shown into the VR landscape, we go ahead and do 50 cross validations with a 60-40 calibration prediction split for our calibration and our respective prediction errors. And we can see what these trends are. The This data set was previously outlier cleaned by the autonomous algorithm, and so we can compare our results with the autonomous algorithm. So this video is for the moisture analyte. The Prism X glyphs don't change because they're just the spectra, but Prism Y glyphs do change relative to the analyte. So here's our Prism X glyphs, and then the Prism Y glyphs, and the composite glyphs. And we're using the PCA score plot, so we have the PC UI in the background. And so you can see there's two obvious, very large glyphs on the Prism X, probably X outliers, very large Z values relative to the rest of the distribution of the training set by the very small, light-colored glyphs. And so here we have some of our larger Prism Y glyphs, but relative to the Z-score, they're not all that big, not like those Prism X ones. And so those two samples, 75 and 77, are not these larger Prism Y glyphs. As we'll see, they're some of the smaller ones. And here they are, the Prism Y glyphs, sample 77, 75, very small. So now we'll shrink down these Prism Y glyphs, and we're going to move over to the composite, and it'll be what we expect. The sample 75 and 77 glyphs will be fairly decently sized. Z-score is 4, and because of the large Prism X scores. And so we're going to throw away one of those, the larger of those samples, 75 and 77. And there it goes. It's now been removed from the data set. The VR landscape's been recalculated. And this says sample 76 now because we're lost a sample. We're only at 79 samples now. And you can see its Z-score is even bigger at 7. And now we'll move on to the Prism X or Y scores plots. And here are 76, not too bad. So not a Prism Y outlier and Prism X outlier, so we will end up removing that. Let's double check. Yes, that is the biggest composite also. So we throw that away. So now the next shot is with 7 samples removed. You can say these seem pretty big, but you can see their Z values are only 3.8 and 3.1, and they were all part of a local cluster of similar sized glyphs. So chances are there's no outliers there because, like I said, you'll always have larger peripheral Z values. And because of their spatial position, they're not outliers. And so you can see here they're part of a local cluster. So we concluded that, okay, after these 7 samples, using the same type of thinking process to remove the first 2, we are now outlier cleaned. So as a recap, on the left are the Prism X, Prism Y, and Prism glyphs before any samples were removed. And on the right is after the final sample removed of the 7 samples that were removed. And you can see, well, you can't see that, but some of the Z-scores are bigger than 3 sigma, which you would normally think would be an outlier if you use 3 sigma as a threshold. But if you look in investigating it, we saw that there are not that big. They're not that much bigger than 3. And there are less dark shaded glyphs, meaning there aren't so many big Z values. And of those that are darker shaded, they're less isolated. That is, they belong to some local clusters. So chances are that they are not outliers. And so we will call that our final set. Here's how we did. We removed 7 samples from the 80 with regard to the moisture content. And you can see the first 3 samples, 75, 77, and 71, are the same first 3 samples removed by the autonomous algorithm. It only removed 5 samples, and after that we do deviate. And so down here are the prediction error and the root mean square of calibration errors. relative to the norm of the PLS, latent variable models. And so we can see what the trends are. And you can see the initial set, the dotted line, versus the autonomous prediction errors and R-squareds of the dotted dash, and then the VR is the solid, that the autonomous and the VR both improve the training set quality versus no outlier removal. And with the VR, we got some extra additional improvement without really decimating, with just 4 more instead of 2 more. So not much of a decimation of the original calibration set. This is our second VR project dealing with outlier detection, and it is going to be in the Journal of Chemometrics.